Hi, my name is Michelle Hills, and I teach at the Science and Math Academy. I currently teach Algebra 2 to the 8th through 11th graders here at SMA. Good morning, guys. Your bell works on the board. I'd like you to get started on that. All right, who would like to come work it? Volunteers? All right, Rowdy, come on. You mark it for me. Talk loud so they can hear.
Affected it to 9 times 10, and affected 9 to 3 times 3, 18, 2 times 5.
Explain it loud.
Then I wrote it in a square root sign, 3 times 3 times 2 times 5 times x to the 8. Then I took out this pair and put it out here. And I took out the x, put x in 4. 2 times 5 equals 10.
Very good. Thank you, sir. Question for you. Yesterday we talked about a specific time when we have to put absolute values in roots. When is that? When do we have to put absolute values in roots?
When a odd root makes a when a even root makes an odd power.
Right, when we have an even root that makes an odd power. What is the root in this problem here? What type of root?
Even.
Square root, correct? Okay, so it is an even root, but what kind of power did we get out?
Even.
An even, so we don't have to worry about it. Why do we not have to worry about it?
Because
Okay, yes, because it's not odd, but there's a reason
the
behind
even
it.
power is just going to make a positive anyway.
Because an even power, go ahead, finish it up for me. Is that what you're going to say?
Yeah, because the even power is going to make a positive number.
Right, because an even power will always make a positive number, so we don't have to worry about the restrictions on putting those absolute values. Are we okay? Okay. I want to compare the difference in this problem versus this problem. There's several differences. I want a hand up. Or several hands. I want an example of what is different in that problem, Amro.
One's an equation and the other one's an expression.
One's an equation, one's an expression, okay?
That's not even inside the square.
Okay, that's not an even power inside the square root. That's a difference. Anything else? Go ahead.
The numbers are like not as big as the others.
The numbers are not as big as the others? Yes. Okay. So Amro said that it's one's an expression, one's an equation. Okay, can someone explain what do we do differently when we have an equation versus an expression? Or vice versa? Go ahead, Minion.
In expression, you simplify, but in equation, you solve.
Very good. Tyron, what does to solve mean? What does solve mean?
Like set it equal to 0. Oh, subtract.
Set it equal to 0, not quite. Anybody else?
Find what x equals.
Find what x equals. Isolate the variable, right? Okay. So today we're going to talk about solving square roots. We're not going to actually solve this problem, but I wanted you to see the difference. We've talked about simplifying, and now we're going to go into solving square roots. So before we go into that, I want to look at this example from London, England. This is the Big Ben clock. Anybody ever heard of the Big Ben clock?
Yep.
When we did class flow online, we saw the Big Ben clock. If you were here when we did that. This clock is a clock tower. It's this one right here. Okay, it's 316 feet tall. It's a very big clock. If you look, it's almost as tall as most of the other buildings. Okay, which I think is a big for a clock, right? And the clock is driven by a 660-pound pendulum. Does anybody know what a pendulum is?
It goes
Oh,
like this.
It's a big thing that swings back and forth.
Swings back and forth. Something that swings back and forth. Very good. And that's what drives this clock. The relationship between the pendulum's length, L, and the time it takes for the pendulum to swing back and forth is called a period. Okay? So the time it takes to go one back and forth, okay, is called a period. And this is actually an equation that people who make clocks and do things like that have to use to find out the length of the pendulum or the time it takes for that pendulum to make a period. So this is actually an example that does. This is actually what the pendulum looks like. Let's see if it'll pop up here for us and sounds like. It's 660 pounds. So, I mean, think about how much you weigh and multiply to get 660. It's very big. And it just swings back and forth. That's what drives it. So, Nothing big there, but just something little for you to have an example. All right, so we're going to go into solving. Let's go to page 724. Let's look at letter C. All right, we want to solve this equation. We've solved equations before, right? No big deal. You move, how do we solve equations? You isolate the variable. But what is different about this equation than what we're used to?
There's a square root in it.
There's a square root in it. That's a pretty big difference, right? So we need to talk about what to do when we have a square root. First off, before we even mess with the square root, what do we need to get rid of, or what do we need to move?
The 8.
The 8 is messing up with the square root? The 4, right? Because the 4 is attached with the square root. How do I move that 4? Go ahead. Divide by 4. Because remember, this is 4 times something. Now, some people think, let's distribute the 4. It may have crossed your mind. Okay? You don't want to distribute inside of the square root. Okay, so we're just going to divide by 4. So everybody, let's divide by 4. Divide by 4. Okay. But what do my rules work? Properties of equality tell me I have to do what? I have to also do it to the other side. Okay. That is called an inverse operation. We've talked about inverse operations. Multiplication. How do we undo multiplication? Divide. How do we undo subtraction? Add. So how do we undo a square root? Square it. Okay, that's called an inverse operation. Now, in chapter 8, we discussed rational equations, where the x was in the denominator. Y'all remember that? And we had to get the x out of the denominator.
Yeah.
We also talked about how there's some solutions that sometimes don't work, so we always have to check them. Remember?
Mm-hmm.
So we have to check these equations. What are they called when the solutions don't work?
No error.
Not no solution, because it may have one that works.
No.
Starts with an E, yes.
I forgot how to go.
Extraneous. Extraneous. Very good. Extraneous solutions are solutions that do not work, okay? So we're going to check this equation. How do I check an equation?
You plug it in.
Plug it in. Let's go. Plug it in for me. So we get 8 equals 8. Is that true?
Yes.
Yes. So our answer is correct. All right. What'd you do?
Instead of square, squared like your one outside.
You squared like both sides. That's what you did. Okay. That's fine. The only thing, Kobe, I'm going to tell you is when you're checking, because that's common, and a lot of people too would have divided by 4. Okay, that's common. The only thing with that is you want to make sure that you kind of want to just mess with this side and this side when you check. Okay, because we're trying to see if this really does equal this. Do you see what I'm saying? We don't know that that's true yet until we check it. It may be greater than or less than. Okay, so try to just stick with one side and simplify those sides and then see if they equal. It's not wrong. It's just not preferred. Okay. All right. Go to your stations. Don't flip it up until I tell you to. Kristen and Marty, look over here. Go whichever one you want. There's 15 of them around the room. I think so. All right. Are you ready? Let's go.
8 squared.
I'm gonna hold it up.
8.
Make sure you close the flap when you're done.
Negative 3 minus x.
Alright, so 46, 36, 6 equals.
Okay, so now you probably move the 4 in, maybe?
I think you would subtract the 4 on both sides.
Yeah, okay. And then it would be left with negative 3x equals 1020. And now you divide by negative 3.
None of these answers have decimals.
Oh. I'm still writing it.
Minus 17. Am I?
I guess we get rid of square roots, right?
Wait, what?
Hey, you got it, bro.
28. Think about 28. Is it positive 28 or negative 28?
Negative because you subtract.
Negative.
Okay, so think about what multiplies to give you 28, your factors of 28.
Negative 24 and I mean -4.
Will that give you your 3?
Yeah.
Are we ready to calculate?
It's like the third one we did today.
X squared minus 36 equals 4x minus 28.
So you got x squared plus 3x minus 28.
And add 28.
Looks like
That's 1 8 to 36.
you move it until you gotta distribute everything and then move everything. No, go ahead and distribute that.
X minus 10, so divide by 7, and that'll be 8
It says we are on a roll right now.
Good.
X
Keep
minus
it
10.
going. Make sure you push it. But look what happened. You have a square root here, but he's not with the square root. So before you square, you have to do what?
You gotta add that.
Add that x over there. I began by doing a simplifying radicals problem that students could review skills that they did yesterday. And then we moved into doing a couple examples, looking at a real life example of the Big Ben clock that shows students that square root functions are actually used in the real world, which is important in mathematics because many students feel like we throw all this math at them and they don't know what to apply it to. So I started off with that, and then I went into doing a couple of examples and letting them use their partners to work some problems on their own so that they can encounter some computational issues so that then we can go through the different ways to solve those. Then I decided to do a scavenger hunt today. The reason I did a scavenger hunt is because a lot of students, especially in this class, I find that they get tired and sleepy because it's second block, it's getting to that mid-morning, they're hitting their low, and so I like to get them up and moving around. And then as well as them talking with one another, I find students learn so well from each other because they're collaborating amongst themselves. A lot of times they make the same problems, or it's something different about a student helping a student rather than a teacher helping a student. And so I decided to do the scavenger hunt because it's really important for students to practice the skills that I just taught. And if they can practice them right away, then they can go home and do it again by themselves and really find out if they are making other mistakes or not. All right, give me attention for just a minute. So today we talked about solving radicals. Y'all saw square roots and cube roots. What else did you see? Fifth root? 100th root?
No.
Did that scare you when you opened it up?
No.
No?
It was easy
That
one was easy.
Once you did both sides, it eliminated.
Right. So that was easy. It looked like it was going to be hard because it was 100th root. But once you just did the 100th power, it eliminated it altogether.
You did that on purpose to scare someone.
No, I just showed you that you can actually do something like that. So, we've talked about simplifying radicals. We've talked about solving radicals. Tomorrow we're going to go in to do some more operations with radicals, multiplication, division, things like that we've already talked about. We talked about that yesterday a little bit. We're going to go into some more detail tomorrow with solving them. Okay, so we're going to kind of add on a little bit.